Hello everyone, Michio Kaku here. And today we're diving into one of the strangest and most chaotic announcements NASA has made in recent memory. For weeks, the astronomy community has been buzzing about what NASA promised would be the sharpest, highest resolution images ever captured of the interstellar object 3I/ATLAS. Billions of dollars in spacecraft, satellites, and telescopes, all focused on a mysterious object hurtling through our solar system at an extraordinary speed. And finally, NASA unveiled those images during a live broadcast, accompanied by a panel of scientists, a set of carefully worded explanations, and a dedicated segment for public questions they may very well regret having agreed to answer. Now, before we start unpacking the pictures themselves, the first thing I want to highlight is something theoretical physicist Michio Kaku once said. Every time we observe something new in the universe, the rules get rewritten. That line has been stuck in my head for the past month because if there was ever an object forcing astronomers to rewrite a few rules, it's absolutely 3I/ATLAS. And after looking at these images, NASA's, amateur astronomers, and everything in between, you'll understand exactly why. Let's start with the introduction NASA gave during their stream. It was clean, rehearsed, typical NASA PR. They talked about the uniqueness of 3I/ATLAS, its hyperbolic trajectory, and how unprecedented it is to have this many instruments aimed at an interstellar visitor. They played soft orchestral music in the background, showed their montage of probes flying through space, and then they finally revealed what they claimed was the best visual data ever collected of this object. And what did we get? Essentially, a glowing pixel surrounded by fuzz, a foggy blur, a cosmic smudge. And look, I want to be fair. Some of these spacecraft, like the Mars Reconnaissance Orbiter, weren't designed to photograph fast-moving interstellar objects. They're optimized for looking down at Mars's surface, not tracking something racing through the inner solar system. But still, when NASA hypes up the clearest image ever captured and then delivers something that looks like a street lamp glowing through thick London fog, you have to expect a certain level of disappointment. And as we get deeper into this video, you'll see exactly why that disappointment turned into public frustration. So let's jump into the first batch of images NASA pushed out. The Hubble shots, taken back on July 21st. Back then, 3I/ATLAS had just been discovered, barely 3 weeks. Hubble zoomed in from millions of miles away and gave us, well, something that's technically recognizable as a comet-like object. The core was bright, fuzzy around the edges, with the bare hint of an extended coma drifting outward. But once again, nothing particularly spectacular. And at this stage, astronomers shrugged and said, all right, Hubble wasn't designed for fast movers. Fair enough. Then NASA showed the James Webb Space Telescope images, taken August 6th. You'd think, okay, Webb is the best infrared telescope ever built, a $10 billion masterpiece operating in deep space. Surely Webb could give us something jaw-dropping. But no, all we got were a handful of pixels arranged in a vague smear, like someone took a pencil and gently rubbed it across a page. No sharp nucleus, no clear tail, nothing that looked even remotely better than what amateur astronomers can capture from their backyard observatories. And this is where things started to get interesting, because right after showing the Webb images, NASA transitioned into their premier highlight, the Mars Reconnaissance Orbiter high-rise image taken on October 2nd. They hyped this one heavily. They teased it. They let the suspense build. They played dramatic music. Then they zoomed in and boom, there it was. The same glowing, foggy blob, just slightly sharper, with a small sunward bulge on one side that they identified as the coma being pushed toward the sun. Now, this high-rise image did give us one important detail: scale. Using the brightest pixel as a reference point, NASA estimated that the nucleus of 3I/ATLAS is somewhere between 1,400 feet and 3.5 miles in diameter. That's a massive range, by the way. When you're estimating something could be the size of a skyscraper or the size of a mountain, that's not exactly what I'd call precise measurement. And to make things more complicated, some independent researchers have proposed sizes as large as 50 kilometers across. NASA dismissed those claims, but when your own images look like cotton balls floating in deep space, people are naturally going to want more clarity. At this point in their stream, NASA shifted into a more cautious tone. They emphasized potential errors, uncertainties, and limitations of each instrument. They used their favorite phrase, complex plasma environment, several times. And that last part is important because plasma is the one thing mainstream science commentators, astrophysicists, and alien ship theorists alike often avoid talking about. Plasma introduces magnetic fields, electric fields, charge interactions, ionization processes, things that complicate the neat textbook picture of a simple comet. And here's where Michio Kaku's perspective becomes relevant again. He has talked for years about the universe being fundamentally electrical and plasma-driven on colossal scales, and that understanding plasma behavior is crucial for interpreting cosmic structures. Yet in all of NASA's commentary, they barely touched on what plasma might mean for the strange jets, inconsistent tail directions, or rapidly shifting coma shape we observe around 3I/ATLAS. They sidestepped the deeper implications entirely. But as we move past NASA's official data dump, things took a turn, because the next section of NASA's stream showed images from amateur astronomers. And these were a completely different world. Instead of blurry pixels or vague blobs, we saw sharp tails, clear jets, structured outflows, and even sunward-facing and anti-sunward-facing activity captured within days of one another. The detail was incredible. And the price tag? Maybe $5,000, $10,000, at most $30,000 for the most serious hobbyists. So let me ask the obvious question. How is it possible that someone in their backyard observatory in Spain, Chile, Arizona, or Australia can capture sharper, clearer, more consistent images of 3I/ATLAS than the most advanced space telescopes ever made? This is where the public frustration boils over. NASA wants you to believe their low-resolution images are simply an unavoidable limitation of the instruments. Not a data selection issue, not a processing issue, not an oversight. But the amateur data proves beyond a doubt that 3I/ATLAS is fully capable of being imaged with clarity. And this is where our journey begins, because in the next parts of this video, we're going to dive deeper into the contradictions, the unexplained tail behaviors, the plasma-rich environment NASA keeps avoiding, and what all of this means for understanding one of the strangest interstellar visitors we've ever seen. Stick with me, this gets a lot more interesting. All right, let's dive right into the section that caused the biggest wave of confusion, and in my opinion, the biggest gap between what NASA showed and what the public expected. Because once NASA finished showing the high-rise image and their scale estimation, they transitioned into imagery from MAVEN, Punch, and the Lucy spacecraft. And that's where things started to get strange. Not just scientifically strange, but visually, logically, and narratively strange. Everything about these images raised more questions than answers. Let's start with the MAVEN ultraviolet image taken on October 9th. NASA displayed it proudly, pointing out the bright central pixel representing the densest part of the coma, an area that, according to their scale bar, spans roughly 33,000 miles. That number alone is wild. But what caught my attention wasn't the size. It was the brightness gradient, the distribution of hydrogen emissions, the way the coma almost looked electrically inflated outward. It didn't match the typical ultraviolet signature of a standard comet outgassing volatile materials. Instead, it resembled something more chaotic, something shaped by ionization, solar-wind interaction, and charge exchange processes. And if you've read any plasma physics at all, or if you've heard Michio Kaku talk about how cosmic plasmas behave, you'd recognize immediately that electrically charged dust and gas don't just float outward evenly. They twist, they react, they pulse, they form filaments. Yet NASA avoided using the word plasma to describe anything in this image. They stuck to words like coma, gas, expansion, and sublimation. It felt like they were deliberately keeping the interpretation simple, even though nothing about the MAVEN image was simple. Then came the punch composite images, and if the MAVEN data raised eyebrows, the punch images blew the eyebrows clean off. On the screen, NASA showed a faint object with a tiny but noticeable tail extending off to one side. This tail was short, stubby, almost cartoonishly small compared to what amateur astronomers would capture later. But there it was, an unmistakable anti-sunward facing tail. But here's the thing. Remember that high-rise image from just 7 days earlier? That image showed what looked like a sunward-facing bulge, implying the coma was being pushed toward the sun. So how do we go from a sunward push to an anti-sunward tail in the span of a few days? NASA didn't address the inconsistency. They just showed the images and moved on, as if nothing about them contradicted one another. And that brings us to one of the most puzzling moments in the entire live stream, the Mars ghost blob. In the punch time-lapse video, you can clearly see Mars passing through the frame. NASA explained that the bright white smear appearing suddenly on the screen was simply the planet Mars, overexposed, pixelated, and blurred due to the instrument's sensitivity. But if that smear really was Mars, then why did 3I/ATLAS appear sharper than Mars? Why was Mars a blown-out blob while the interstellar object tens of millions of miles away appeared clean and structured in the exact same frame? NASA's answer was that the processing applied to 3I/ATLAS wasn't applied to Mars. But that explanation didn't satisfy anyone. And honestly, it shouldn't. When two objects appear in the same frame of the same exposure, the same instrument, at the same moment, we should expect some consistency in how they resolve. Yet here, Mars, a full planet, looked washed out and tiny compared to the bright, sharp smudge of 3I/ATLAS. That contrast alone was enough to get the public asking questions. And NASA's silence after the chat, filled with skepticism, didn't help. Then NASA showed the Lucy spacecraft image from September 16th. And once again, we saw something different. Not wildly different, but different enough to keep this pattern going. This time the coma seemed expanded on the sunward side. It looked softer, like something being inflated against a flow. Again, completely inconsistent with the punch tail direction. And once again, NASA provided almost no commentary to reconcile these opposing observations. At this point, viewers, myself included, were left staring at the live chat, wondering if NASA itself had fully processed what they were showing. Because instead of a clean sequence of visual data that matches across instruments, we saw contradiction after contradiction. Sometimes the coma bulged toward the sun. Sometimes the tail pointed toward the sun. Sometimes it pointed away. Sometimes there was no tail at all. Sometimes the object looked brighter than Mars. Sometimes it looked like a faint puffball. Nothing was consistent. But then the live stream moved on, and NASA played what essentially became the unintentional plot twist of the day, the comparison with amateur astronomers. Because if NASA's images were inconsistent, murky, and low in detail, amateur astronomer data was the exact opposite. The first amateur photo they showed was from November 8th, after perihelion, and it immediately revealed structures NASA failed to show. A clear anti-sunward tail, several visible jets erupting from the coma, and a sunward-facing jet that didn't match any of NASA's earlier images. The detail was stunning. You could see the orientation. You could see the faint curvature. You could even see subtle differences in brightness across the jets as the object rotated. And remember, the people taking these images were using equipment that costs less than a used car. Then the images from November 9th appeared. And again, the level of clarity blew NASA's images out of the water. The tail was broader. The jets were more dynamic. The coma was more symmetrical. The structure was coherent. These images lined up with one another over time, revealing patterns NASA never mentioned. You could track rotation, you could track directional changes, You could see consistency in multiple amateur observations across multiple continents. Then came November 10th, then November 16th, then November 19th. Each one sharpening the story further. Instead of a blurry pixel surrounded by fog, amateurs were showing a living, dynamic object. Jets twisting, plasma streams shifting, the tail elongating, the coma swelling and contracting. Everything NASA's billion-dollar instruments failed to show clearly. Amateur gear captured effortlessly. And here's where it becomes impossible not to question the narrative. NASA framed their images as the best possible data. Yet the community, armed with nothing more than passion, clear skies, and dedicated equipment, produced better, richer, more consistent visuals than the most powerful space agency in human history. Now, I'm not saying NASA is hiding anything. I'm not jumping into conspiracies. But I am saying that NASA's imagery and explanations left too many gaps. Gaps filled almost immediately by the amateur community. And that's exactly why, in the next part, we need to talk about what all of this means. The plasma behavior, the inconsistent tail directions, the nature of interstellar visitors, and whether NASA's simple "it's just a comet" explanation truly matches what we're observing. So now that we've gone through NASA's images, the contradictions, the amateur photographs, and the stunning differences between them, let's talk about what all of this actually means. Because the question hanging over this entire conversation isn't just, why do amateur images look clearer than NASA's? The deeper question is, what is 3IATLAS really doing out there? And why does almost every data set, professional or amateur, show behavior that doesn't fit neatly into the simple "it's a comet" box NASA keeps pushing? Let's start with the most obvious clue, the plasma environment. If you pay close attention to the amateur images, especially those from November 8th, 9th, and 16th, you see something profoundly unusual. Jets that should behave predictably under solar wind pressure instead twist in different directions. A sunward-facing jet appears consistently in multiple images. On other nights, anti-sunward jets dominate. The coma inflates, then collapses, then inflates again. Tails appear short, then long, then ragged, then smooth. These aren't just minor aesthetic differences. They're signatures of intense ionization, electrical effects, and magnetic interactions, all the things NASA avoided discussing during their live stream. And that brings us back to something Michio Kaku has emphasized for years. Space is not empty. It is a sea of plasma, charged particles, magnetic fields, and electrical currents shaping nearly everything we see. When an interstellar object like 3I/ATLAS cuts through that environment at such high velocity, it doesn't just leave a vapor trail, it creates turbulence, electromagnetic sheaths, charge separation zones, ion tails that twist like ropes in the solar wind. Everything happening around 3I/ATLAS points toward a complex plasma-dominated structure, not just sublimating ice. And here's the thing. The amateur astronomers captured that complexity far better than NASA did. Their telescopes didn't see a static blob. They saw an evolving system, rotating, reacting, shifting. They saw consistency over time. The features they captured repeated night after night, matching the rotation period, matching the changes in solar wind conditions, matching predictions based on plasma models far more than traditional comet models. Meanwhile, NASA's imagery looked like snapshots from different realities. One instrument shows the coma being pushed toward the sun. Another shows a tail being pushed away from the sun. Another shows nothing at all. Another shows a giant overexposed blob where a planet should be. If you stitched all of NASA's data together chronologically, you'd think you were looking at 4 or 5 completely different objects, not one interstellar visitor. So the natural question becomes, is NASA oversimplifying on purpose, or are they simply limited by their instruments? My honest guess is a mix of both. Spacecraft designed for other missions aren't optimized for fast-moving targets. But at the same time, NASA seems almost desperate to reinforce the message. It's just a comet. They said it over and over during the live stream. They pushed it before any questions were asked. They emphasized it more than the data itself. And that alone tells you something. Because if everything was as simple as they claimed, there would be no need to insist. The images would speak for themselves. But instead, the community had to rely on amateur astronomers to see the real structure, the jets, the rotations, the plasma trails, the asymmetric coma. And that contrast has defined the entire 3I/ATLAS conversation. But here's what matters most. Regardless of how NASA frames it, 3I/ATLAS is one of the strangest interstellar objects we've ever seen. It is fast, it is bright, it is reactive. It behaves unlike the comets we've studied for centuries. And whether you call it a comet, an interstellar fragment, a plasma-dominated body, or something more exotic, its presence in our solar system is extraordinary. And that's why, at the end of all this, I want to echo something I've said from the start. Do your own research. Don't rely on a single source, whether it's NASA, me, any other scientist, or any influencer online. Look at the images yourself. Compare them. Follow the amateur astronomers producing incredible work. Look at NASA's gallery and pay attention to the physics, the real physics, not just the safest interpretation. Because when you do, when you lay all the data out, a much richer picture emerges. A picture of an object shaped by forces more complex than frozen gases evaporating in sunlight. A picture of a plasma-rich interstellar visitor interacting dynamically with our solar system. A picture that even NASA's billion-dollar instruments struggled to capture cleanly. As for me, I'll keep following the data. I'll keep updating you as more images come in, and I'll keep asking the questions NASA didn't address, because curiosity is how science moves forward. Like Michio Kaku said, the universe rewrites its rules every time we see something new. And 3I/ATLAS is absolutely one of those moments. Thanks for watching. Take care of yourselves, and I'll see you in the next video.